Welcome to our focus event. We are very excited to be with you. Today, we are going to focus on future computing architectures and Professor Onur's experiences. Welcome, Professor Onur. Thank you for joining us.
Hello, merhaba.
Merhaba hocam. I want to introduce you to our participants in general, in a short way. Onur Mutlu is very successful professor of computer science. He started his college career at Bilkent University in computer science. At the end of the first year at Bilkent, he continued his college career at Michigan University, Ann Arbor. He has taken his bachelor's degree in psychology and computer engineering from Michigan. He has taken his master and doctorate degree in computer engineering from University of Texas, Austin. He worked at top-level tech companies such as Intel, Microsoft, Google, and finally, he is now a professor of computer science at uh, ETH Zurich. These words can be read from internet as well. Let's know Professor Onur Mutlu better. Uh, Professor Onur, can you tell us the story of going to Michigan University? When did you meet with computer first? When did you decide to study computer science?
Okay, that's a good question. Old times. Let me first thank you for inviting me to give this talk at Koç University. It's always good to talk with students who are interested in doing good things into the future. And it's good to meet everyone, of course, online, unfortunately. As you said, I started at Bilkent University, my undergraduate degree. This was in 1996, I think. Before that, I was at Beşiktaş Atatürk Anadolu Lisesi High School in Turkey. And I was always interested in computers. I mean, the first, you asked me when I met computers first, I think we had a Commodore 64 when I was a kid, about 8 or 9 years old, and I used to play games on it and do some programming on it. But I didn't really know much about computers other than using them and programming them and gaming with them a little bit. But I was interested in that, so when I was a student at Beşiktaş Atatürk Anatolian High School, I actually computers was actually one of the things I wanted to study going into the future. But I was also interested in many things. Like I was very interested in molecular biology and genetics, for example, bioinformatics, and also international relations. And I wanted to do all of them. But when I asked my father and my parents what would be a good idea to study, they told me, especially my father told me that I should do engineering or computer engineering because the future is there, and if I can do computer engineering extremely well, I can also branch out into some other areas potentially, whereas it's harder the other way around, he said. And I think I took his advice, and that was good advice, I believe. When I entered the university entrance examinations in Turkey, which you're familiar with probably, that was in 1996. That was how many years ago? 25 years ago, basically. And you needed to select at that time. Basically, you selected which places you wanted to go to, and my first choice was Bilkent University Computer Engineering, and my second choice was Bilkent University Molecular Biology and Genetics. So I was interested in both, as you can see, and I believe I had medicine somewhere also in one of the choices. But in the end, I got into my top choice and decided to go to Bilkent. Well, I guess you have no other choice. If you get into your top choice, you go to your top choice in Turkey. you don't get to choose the next one. So I started at Bilkent, and I liked computer engineering, but I also had the opportunity at the time to go to a foreign country to continue my education. This used to be true at that time. There was a scholarship given to students who do very well in the university entrance examinations. I think top 200 students at the time. I don't think it exists anymore, but it used to be that you could basically choose to go to some university in, I think, 5 countries. I don't remember exactly which ones, but US, UK, Switzerland, 2 other ones I don't remember now. But I decided maybe I should try that because I was interested in many things and I wanted to learn more. So I basically applied to universities in the US and I was a bit late in deciding that I wanted to do that. So I applied to a bunch of places. I got into Michigan and I decided to go basically since it was funded by the Ministry of Education at that time. And I think that was a good opportunity. I took it and I don't regret it at this point because I learned a lot at Michigan. And I was able to branch into other areas as well, like psychology, which would have been very difficult to do, I think, at Bilkent. So hopefully that answers your question. I can go into more detail, of course.
Yeah, it was amazing answer. And you have mentioned you did double major with psychology. How it contributes to your career? Are you using your psychology knowledge even today in your work life or personal life?
Yeah, so that's so basically, I guess the answer is yes. I think sometimes yes, you make use of it based on in people relations, for example, when you work with people or when you try to analyze things that people do. It's very helpful for sure. And there are multiple aspects to this answer, I think. So let me actually tell you why I decided to study psychology. So at the time I went to Michigan. Basically, Turkish government wanted me to study computer engineering because I was computer engineering at Bilkent, right? They were going to support me for computer engineering. But I took a class at Michigan in my first semester from a fabulous professor, James Lloyd Hilton. And I really enjoyed his class. This was Psychology 101. It was a big class, and I really enjoyed it. I said, I'm going to take more psychology classes. And I took another class from James Lloyd Hilton, and that was also a great class. I enjoyed it. It was social psychology. And then I said, okay, this is really interesting. So I should keep taking classes in psychology in addition to computer engineering. And I was doing well. So I decided I will continue learning more about psychology and doing a degree. Before that, when I was at Bilkent, I was actually quite interested in psychology, all aspects of it, both personality and cognitive psychology, neuropsychology. So right now, I think it helps in many ways because, first of all, I think there is a social and personal aspect of psychology that's really useful to understand, to basically try to understand why humans do the things they do, right? I mean, of course, this is not easy, but you can, with some formal education, I think you can have better guesses, in my opinion, and also better guesses in working with people potentially, because as I said, psychology is very social, but there's an organizational aspect to it also. You can form better organizations, in my opinion, if you understand psychology really well. But there's also a very biological or neurological aspect of psychology as well, which is cognitive psychology or neurological psychology, which is really related to the study of the brain, for example, and study of intelligence, study of memory. And I think that aspect is clearly very much related to things like artificial intelligence today or machine learning, because you actually study a lot of different forms of learning in psychology when you take a cognitive psychology class. And I think today in the works we do, sometimes the connection appears. And I always get amazed that humans are such good learners compared to machines today in many aspects. So I think there are some application that we do in that area as well, the cognitive part, and also the neuropsychology part. We do some work in bioinformatics, for example, and I think understanding the biological aspects of psychology is useful in modeling some of the things that we do. So basically, the short answer is yes. The long answer is, I think, maybe not as much as I would like to, because there's a lot of interesting things that you can do in psychology as well that I don't have time for doing. There's an experimental aspect of psychology that's, I think, very, very exciting. But I don't work on psychology directly. As a result, I don't really have time to do experiments, for example.
Thank you. Again, it was brilliant answer. And I want to ask you something. One more thing
Sure.
before our talk in future competing architectures. You are sharing almost all your lectures, talks in your YouTube channel. I recommend everyone who interested in hardware to follow your channel. Probably you should get permission and make an effort to share them. What is your motivation to share them? Your all work in open as an open source.
Yeah, that's a good question. Thanks, and thanks for recommending the courses. Hopefully, other people benefit from it as well. So I think the basic motivation is very simple. We have this knowledge, and it's better to. Wait a second. Okay, I was muted for some time. I think the basic motivation is just to share the knowledge so that the knowledge actually grows overall. There's a saying in Turkish, bilgi paylaştıkça çoğalır, for example. I think I believe in that a lot. That's why I think not just for lectures, but also in a lot of the research work, we open source a lot of our work so that other people can build on it. And I think that's the way we can better help people and a lot of people who don't necessarily have access to these resources all over the world to get to a better position such that they can improve, in my opinion. So that's the major reason why we do it overall. But there's also when I first started doing it, when I started teaching at Carnegie Mellon University in 2009, I basically said at some point, I'm doing these lectures and I'm already giving them. Why shouldn't I just record them and put them online so that others can make use of it, as opposed to just giving them again and again and again and again without having any recording of it. And also I can probably learn from the experience by seeing my older lectures and improving over time. So that's what I said, basically. So we started putting up the lectures from 2012. The earliest lectures are from 2012, but they're not with a very good recording camera. So the better ones are from 2013. So I started teaching in 2009, and it took us about 3 years to decide to put it up. And I think better late than never, right? It's better to do it late than never. I wish I had recorded in 2009 also, actually, because now I want to go back to those lectures, some of those lectures that we delivered in 2009, and look at them and see how we can improve. But I don't have that choice because they're already gone, right? So I think the other reason is really to have it in recording what we have done, and I think it's useful for us as well to improve. But probably it's more useful for others in the world. And I usually get actually messages from people saying that, thanking me for the lectures, and some people are actually using the lectures in universities to teach the students. Some people are supplementing it. Some people are just studying it for interviews, for example, when they want to go to work in hardware and hardware software interface. They use the lectures and study. And I've got a bunch of, sometimes I get emails thanking me because they actually did well in the interview because of the lectures. So I think it's nice to certainly help people. In the end, it's all free, right? I don't get any benefit from it in the end. So it's good to feel that we can actually give back to people who are interested in doing good things in the world.
I am also thankful for sharing this high quality educational resources in open course. And I am sure everyone who watching your lectures are thankful.
Sure. Thank you.
And it's time to uh, talking about future computing architecture.
Okay. No more questions?
If people have personal question to know you better, can ask if they want. If there is no question, we will start future computing architecture, and then there will be again Q&A section, and you can ask your question in there. It can be personal and it can be related to our topic as well.
Okay, that sounds good to me. I don't hear any questions right now, so
you
maybe
can
I'll
write
just
in chat box as well. If you are not writing, we will start.
I have a question. Can I ask?
sure.
Your voice is very low.
Now is it okay? Now,
Better.
okay. Is the programming for the programming is needed more advanced electronic devices? If I mean, if for example your program is advanced, and do you need good electronical structures?
So I think I understand the question. So basically, I think what you're getting at is if you need to achieve very high performance or very high efficiency, do you need more specialized hardware? Do you need to know about hardware? And my answer to that is yes, for sure. Because if you want to build something that's really at the cutting edge, that has extremely high performance, high efficiency, today's hardware, general purpose hardware, is not enough. So if you program Intel processors, AMD processors, for example, even GPUs today are not enough to get you very high performance and very high efficiency on applications that you really want that for. So for example, machine learning is one example. I'll give some examples in this talk also. If you want to do a self-driving car, for example, or if you're very much constrained in terms of power in a device, you really want to have a specialized hardware that's dedicated for what you're doing. Not necessarily fully dedicated, but customizable for what you're doing. And that requires your programming to take advantage of, as well as to understand the characteristics of the hardware. So we will talk a little bit more about this during the talk. And that sort of specialization is going to be more important in the future. So to put another way, I think if you're satisfied with the performance and efficiency of general purpose processors, then you don't need to, I think. But I should also say that if you're satisfied with the performance and efficiency of general purpose processors, then probably you're not pushing the cutting edge of the problems that you're solving or research, for example. Hopefully that's clear.
Thank you. Thank you.
Sure, you're welcome.
We can begin, I think.
Okay, sounds good. Yeah, let's start then. And feel free to ask questions also during the talk. I think we have about 40 to 60 minutes for the talk, right? And I usually talk a lot, and it's usually high bandwidth. So a good way of stopping me is really by asking questions and stopping me that way. And this talk usually leads to a lot of questions, so hopefully it'll be interesting to people. So I'm going to talk about future computing architectures and focus on challenges and opportunities. Before that, let me quickly start. I'm not going to spend a lot of time over here because I think we've already discussed some of this. But as we mentioned, I'm a professor at ETH Zurich for about 5 to 6 years now. Before that, I was a professor at Carnegie Mellon University for about 7 years or so. I still have students at Carnegie Mellon. My last student will graduate this year, basically. And we've already discussed a bunch of this. I work in computer architecture, computer systems, hardware security, and bioinformatics. And we will talk about some of the things that we work on in my group. My current research mission is to build fundamentally better architectures. Essentially, this could be any type of architecture. We look into all components in a system, both processors, accelerators, memory, storage, specialized processors. We work in the hardware-software interface. We look at computing platforms, which is the subject of this talk, bioinformatics, and hardware security as well. So our interests are quite varied, actually, and I find it quite exciting to work on these areas. We also work on the macro scale, like a larger scale of connecting these different computers to each other as well. Look at interconnects, for example, and scheduling issues at the higher levels, but this slide doesn't cover them. These are 4 current directions that we are examining in my group, and I'm going to go into detail on 2 of them. We won't have time to talk about all of them, but we're going to hopefully talk about making systems and architectures more secure, reliable, and safe, fundamentally better. Talk about fundamentally energy efficient architectures, which by definition need to be memory-centric or data-centric. We probably won't be able to talk about low latency and predictable architectures, but this is also very, very important. For example, if you have a device that can do genome sequencing, you really want low latency in that device so that you can give it to a doctor and the doctor can sequence someone's genome and quickly decide what kind of action, what kind of drug, for example, they should administer to this person so that they don't have any complications and they can specialize or customize the drug delivery to the person's characteristics, genomic characteristics, plus other characteristics as well. And this fundamentally requires to be low latency. Today, you could do things like this, but it takes days or weeks to get an answer from the genome analysis, for example. We would like to minimize this to 1 second or seconds so that we can hopefully help make medicine and public health much better. And this is clearly very important in the entire world today when we talk about COVID-19. So low latency and predictability is very important, I think, for devices that we rely that we build our lives on, let's say. And then we also look into architecture designs for really important applications like artificial intelligence, machine learning, graph analytics, genomics, medicine, and health. So we'll talk about a couple of these directions. Let me talk about what I mentioned earlier. So this is the transformation hierarchy of computing. You have a problem and you want to solve it. And we have built a hierarchy of transformation that goes from problem to algorithm, language, system software, hardware software interface, microarchitecture, logic, device, and electrons. And we built this so that our lives are easier to actually program, for example, without knowing what's underneath, right? So the narrow view of computer architecture, for those who do not necessarily know, is it's really about the hardware-software interface and the microarchitecture. But I take the expanded view of computer architecture. Today, if you want to maximize the performance and efficiency, as I mentioned earlier, we really need to think across the stack, basically. Think about the algorithms and languages and system software and hardware-software interface, logic and microarchitecture, and co-design all of them together so that we can maximize performance and maximize efficiency. And I'll give you examples. Again, genomics is a very good example of this. If you want to maximize the performance, minimize the latency, and maximize the energy efficiency of this genomic device that sequences your genome, and that can help you make a decision related to, critically related to your health, for example, you really want this algorithm to device co-design so that you can maximize efficiency, maximize performance. Okay, so that's my axiom basically in computer architecture. To achieve the highest efficiency and performance, we must take this expanded view of computer architecture. And we should co-design across the hierarchy from algorithms to devices and specialize as much as possible within the design goal. So our work in computer architecture designs for artificial intelligence, machine learning, graph processing, the genomics and bioinformatics are all examples of this, which we will talk about, hopefully, if we have the time. So these are some current research topics that we are examining in my group. This is a busy slide, so I'm not going to talk a lot about everything clearly. But we're doing broad research spanning applications, systems, and logic with architecture at the center of it. But we actually are quite comfortable looking into circuits and devices and also looking into algorithms and customizing them. So it's a broad research, as you can see. And these are some directions that we follow, but I'm not going to talk about them in detail right now because I'm going to give you some examples. This slide is just a complete slide that looks at essentially a lot of the things we do, maybe not all the things we do. And this is my group. This is a snapshot from maybe late 2019 or early 2020. You can see there are a number of researchers. Right now, we're around 40 people, and this is the motto of the group. And you can visit the website. This is a more recent snapshot from December 2020, and we have our newsletter. We released the newsletter in January 2021 that talks about the work that has come out of our group in 2020. So if you're interested, you can take a look at this newsletter. There's a lot more material over here about our recent research than what I'm going to talk about today. Let me tell you a little bit more about my thinking so that what comes later hopefully becomes clear. So I believe in this a lot. And this is actually, I forgot to say, but this is one of the reasons why putting out our lectures online is useful as well, because it helps teaching across the world. But I also think it helps research across the world because people can build on what we put out online to do better cutting edge research, hopefully, because a lot of our courses actually related to research. And I strongly believe that teaching drives research, and then research in the end drives teaching. And then this is an endless loop. So what do I mean by this? I think these two things are the two sides of the same coin. So when I teach, for example, I talk about things that everybody knows, let's say. I just deliver them as an educator, right? But when we do research, when you actually have a publishable result, you change the world, essentially. But you're also an educator. What you do is, whenever, for example, when you go at a top conference and present your research results, you're really educating the community and everyone about something that no one else knew about because you found out about that. So research and teaching are both education in the end, and they amplify our knowledge in the world and hopefully make the world a better place overall. But this is also an endless loop because after you do research, you talk about in the classes. I actually talk about some of the topics that I'm going to talk about today in my undergraduate class, first year class at ETH in digital design and computer architecture, and introduce students to research that way. And also teaching drives research as well, because when you actually teach about some fundamental topics, you figure out what to do next. So I think this is an endless loop. And this is also true because students, for example, some of my students have been, some of my PhD students have been my students in my class in second year or first year or third year in their undergraduate degrees. So they become researchers because they actually learn about research in classes. So this is actually very interesting. I can talk more about it, but we don't have a lot of time. So in our group, we focus a lot on insight and new ideas. And I like new ideas a lot because in the end, the world progresses if you keep generating new ideas, right? Progress stops if you don't think critically and generate new insight and new ideas. So that's really important to me. Okay, I'm not going to talk more about this, but if you're interested, there's a variety of videos we released, as Ahmed mentioned earlier. And these are some example videos that talk about some of the overview talks that we have delivered. This talk is actually a mixture of some of these, but some of the other talks are more specialized. And you can find all of them in our YouTube channel. And if you're more interested in my views on computing research and education, feel free to ask questions at the end of the talk or somewhere in between. But I also gave an interview to a couple of students, PhD students from University of Southern California. They interviewed me after this conference in 2019. And they asked very good questions to get my opinions on computing research and education. So you can take a look at them or listen to some of the speeches that we have and some of the other slides that we put out. Okay, so hopefully that was interesting. And everything that I mentioned in this talk is open source online on our webpage. You can find them. And you can also find some of the talks, as I mentioned, in the YouTube channel. So with that, let me start. Any questions so far? Or should I just jump into the topic? Okay. I don't hear questions, so I will jump in. Feel free to write things on the chat also, and you can tell me when to look. Okay, so I'm going to talk about future computing architectures, but I will start very fundamental with the question, why do we do computing? And I think the answer to this is very clear: to solve problems. The reason I wanted to become an engineer, computer engineering and computer scientist, I think they're both the same actually, in my opinion, is to solve problems. And engineers solve problems in the world. So rewording this answer, why do we solve problems? So that we can gain insight. And this was also mentioned by Richard Hamming, who introduced Hamming codes, for example, in a seminal work in 1960s. And I would recommend you take a look at it if you're interested. So if you extend the answer, why do we want to gain insight? Essentially, we want to enable a better life and future. And hopefully better in the sense that it's better. Unfortunately, people can use technology for bad reasons also. But we're going to ignore them for now. Technology is actually agnostic to ethics, right? Or morality. You can use it for good or for bad, but we're going to assume that our goal is to do good rather than bad. So how does a computer solve problems? And today's answer is by orchestrating electrons. In today's dominant technologies, we need to orchestrate electrons to make sure that electrons do the things that we want them to do. And that brings us to the transformation hierarchy. How do we get electrons to solve the problems that we want? We have problem at the top, we have electron at the bottom, and we don't speak the language electrons speak, and electrons don't speak the language we speak. So we have a communication problem, right? Essentially, we need to do something about it. And what we did about it is really this transformation hierarchy. We translate the problem to an algorithm that gets translated to a program in a language that gets translated and executed on a system software and run on a hardware-software interface, which is implemented in a microarchitecture, which is implemented by logic gates, which is in turn implemented by transistors and devices, which in turn operate based on electrical and electronic principles, right? And as I mentioned, this is the narrow view of computer architecture, and I would like to focus on the more expanded view. So let me quickly talk about computer architecture, since not many of you may know a lot about computer architecture. So let's start with this first. Computer architecture is a science and art of designing computing platforms, hardware, interface, system software, and programming model. And this is a broad definition of computer architecture. And I view this as science and engineering, a methodical way of studying, but it's also art, very much similar to real architecture, building architecture, because you don't know the future necessarily, right? You're designing this computing system and somebody will use it maybe 30 years, 20 years down the road, or even 5 years down the road, or 2 years down the road, and you don't know what they will run on the system. So you need to be artful about how you design the system also. You really need to make use of your experience. You cannot model everything with science and engineering because we don't have the capability to model even 6 months into the future, right? Today, let alone 20 years into the future. So it's really, I like this aspect of computer architecture a lot because it's really a combination of science and art in the end. And the goal is to achieve a set of design goals. Basically, the design goal depends on what you would like to do with the computing system that you're designing. For example, you may be designing a supercomputer to achieve the highest performance on Earth on 3 workloads, X, Y, Z. For example, matrix multiplication could be one, or weather prediction could be a more general, bigger workload. Yeah, so these are some examples. And this is clearly one design point. And this requires you to actually maximize your performance. And then another potential design point could be, you would like to achieve the longest battery life at a form factor that fits in your pocket with cost less than some dollars. Is there a question? I hear some. Hello? Okay, so I'll continue. So that could be another design point, right? This is like a cell phone, for example, longest battery life at a form factor that fits in your pocket. And then the goal is not high performance on these big workloads anymore, right? Another design point could be the best average performance across all known workloads that you care about at best performance cost ratio. This is more general purpose designs, right? Intel, AMD, for example, design computers that are good at essentially, that are good at executing everything, but they may not be the best at anything. So this is more general purpose. The first one is supercomputing. The middle one is more mobile computing. And then you can become more specialized also. Maybe your goal is just to accelerate machine learning, for example, specific forms of machine learning. So it really depends on your design point, basically. And these are very different design points, and they look different, but many fundamental principles are actually similar in the end. So let me give you some examples. These are clearly platforms that you use. These are different platforms and different goals, but they're all built with basic fundamental building blocks, let's say. This is another example. Clearly people use it, right? And that has very different constraints, but it still has basic fundamental principles. But the way those fundamental principles are applied may be different, because here, for example, the battery life is a big concern. Potentially security is a big concern, a bigger concern than others, perhaps. I don't know. This is another example, right? A self-driving car. Of course, this is a joking example. Ideally, we would like to be able to achieve this, meaning we would like to be able to trust our system such that we could self-drive like this without thinking about it. But unfortunately, we are far from it, basically. We cannot trust our systems this much today, because we might quickly get into an accident if we trust our systems this much. So we will talk about security issues, for example, related to memory later on. And keep that in mind when you see this example. So if you would like to achieve a self-driving car, you really would like it to be robust and secure so that it doesn't make any mistakes in this case. So this is another self-driving car. This is from Google. And you can see that there's a lot of computing that's dedicated at the back end of it. And ideally, you want to minimize this, right? You don't want a huge server farm like this inside your car because it's expensive and costly, etc. So this is a data center. Clearly, this is important also, and that's designed for some workloads. And this is a supercomputer. This is one of the fastest supercomputers of its time, Tianhe 2 from China. These are different platforms and designed for different goals, but again, their fundamental building blocks are similar. This is one example that essentially proves my axiom earlier. This is a machine learning accelerator designed by Google and released in 2017. They call it the Tensor Processing Unit. And its fundamental design principles are based on systolic array execution. If you take my YouTube lectures, for example, you will see systolic arrays over there. It's essentially fundamentally a systolic array. But their goal was to actually design this hardware so that they can accelerate their software, machine learning software in the data centers. So they said, we're executing the software, it's consuming a lot of energy, and it's not getting good performance on general purpose processors. So we're going to build our own hardware to accelerate the machine learning workloads that we're executing, because it's very important for us. And they actually became a hardware company by designing these workloads, designing these boards, as you can see, and chips that can accelerate machine learning. So these are very specialized for machine learning, for example. This is another example from Tesla. Tesla is a car company, right? Why are they building chips? Well, they're building chips so that they can execute their software much faster and much more efficiently. And they can customize their hardware for their software so that they can do self-driving better. So these chips, for example, are good at doing machine learning, pedestrian detection, etc., that are really critical for safely driving self-driving cars, right? And you can see that there are two chips that are concurrently operating, executing the same program for better safety. And if you're interested, you can actually look at their YouTube video, which talks a lot about their design. I think these are quite exciting and interesting, as you can see. And these are examples of the axiom that I mentioned. If you are really innovating at the cutting edge, and if you want to achieve the highest efficiency and performance, you should really design hardware and the software and the algorithms together so that you can maximize and specialize within the design goals. And you can see that many companies are doing that. Google is traditionally a software company. Tesla is traditionally a car company, but they're designing their own hardware. And there are many, many other examples of this. Microsoft, Amazon. Pick any company that's doing innovation at the cutting edge today. They're all designing their hardware today, and they're all designing their systems and platforms today, because there's no other choice, if you will. They cannot rely on general purpose processors to execute their workloads. And they also know their workloads very well. So Apple is another example, actually. I don't have it on my slides, for example, but they released their own processors recently, very recently, last month, I think, or maybe this year sometime. Why did they do that? Because they could actually customize the design to their own software, just like these other companies do. And that enables much better systems, in my opinion. Okay, so now that we've covered some systems and axiom, I will also ask, what kind of a future do we want? And again, hopefully the future would be good, not necessarily bad. We can only strive for a good future, and we can try to enable it, right? And I will ask you maybe some questions. This is a bridge that I use in my freshman classes, and this bridge looks nice and secure, right? This was actually on Tacoma Narrows in Seattle. I started the Microsoft Research Computer Architecture Group in 2006 after my PhD, and I enjoyed the beauty of the Seattle area. And I used to go to the Olympic National Park around this area, for example. But I did not cross this bridge because this bridge collapsed 6 months after its construction. And I think this is an important example because you could think of this bridge as a critical infrastructure. And it is critical infrastructure, right? And we're building it. And if it collapses, then we have a problem with the safety, security, and reliability, clearly. This may cause a lot of problems, right? Including loss of life. And I think of computing as even more critical infrastructure than bridges. So bridges are interesting. Yes, they're everywhere. Human beings have been constructing bridges for thousands of years, but they're limited. You don't cross a bridge every day, right? Well, some people do, but in general, you don't spend a lot of time on bridges. But if you actually look at computers, we spend most of our time today on computers, maybe more than we sleep. We spend time on computers. And in some cases, in many cases, actually, it becomes safety critical. And if you actually have problems like this, where computers break, for example, when they're self-driving, then we will actually have significant problems. So computing infrastructure is perhaps the biggest and most important infrastructure that we're designing today. And if you actually have security, safety, reliability problems like this, it's going to become much worse for us in the future. And this is another view of that beautiful bridge that's gone after some time. I actually also use this picture. These are folks who are constructing New York after the World War, and they're sitting on this rod, which looks quite strong. But if a bit flip happens, if a problem happens, they may not be very happy 1 minute later, right? So I think of security as preventing unforeseen consequences. You can also think of safety this way. And I believe this is an important definition of security. And we're going to talk about security a lot because I think we want a future that's dependable, reliable, secure, and safe, which requires us to actually make our computers reliable, secure, and safe, and dependable. So I'm going to talk about that. And I think this is very important. So the second part is we want a future that's nice, meaning sustainable and efficient, that looks like this. And I don't think we want a future that looks like this. I think actually, let me put it this way. We want the best of both worlds. We want a beautiful future that's sustainable, efficient, and also very productive at the same time, high performance at the same time, because we want to solve those high performance problems. So to be able to do that, I think, again, computing infrastructure is all over the world. We need to make the computing infrastructure sustainable and energy efficient. And I'm going to talk about that as well. So at the same time, we have many difficult problems to solve in the world. They're increasing, unfortunately. Climate is one big problem going into the future. We need to solve it somehow. Cities have a lot of problems like congestion. People who live in Istanbul probably are familiar with this. This is a picture from China, actually. We need to tackle key challenges like intelligence and more understanding nature, for example. We need to figure out how to do a good job in public health as opposed to terribly failing at public health problems that we see. And we need to really understand what we're doing and improve medicine and health overall with better genome analysis, for example. And I think for all of this, we need better performance, higher performance, lower latency, higher efficiency. And I like genome analysis because this is something we have been working on for about 14 years or so now. But the idea is actually to design devices that can do genome analysis extremely fast so that you can actually give these devices or use these devices for life-critical situations, or also do outbreak tracing like COVID-19 tracing, and also outbreak fixing, for example. And we do a lot of work in this area. I'm not going to talk about this in detail, but people may be interested in it. This is a recent paper that we wrote on accelerating genome analysis. And we talk about a lot of different approaches to do this. And again, this is a hardware-software co-design. If you really want to accelerate genome analysis, you really need to design the software and the hardware together. You cannot just say, okay, I have really great software, I'm done, because that's not enough. It's not fast enough. It's not efficient enough. It will buy you maybe 10x, but it will not buy you 100x, 1000x. And today we need more than 1,000,000x speed up and energy efficiency if you want to reduce the time for analysis for to seconds or minutes. And if you are really interested in learning more about genome analysis, you can watch my lecture that was recently delivered. It's online, as you can see, and I talk about more detail in this lecture. And we also have content in our courses on genome analysis. And there, yeah, as I mentioned, this is some of the content that we have on genome analysis with links to particular lectures. I'm going to share these slides with Ahmet later on and put them online on my website also, so you can find the links from these slides. Okay, so basically everything that I discussed so far is we want high performance to solve all these problems. Genome analysis is one example, but climate is another example. Intelligence, machine learning, artificial intelligence are all other examples. And these are some tough problems, and we want to solve all problems, and we want to solve the toughest problems. For that, you definitely need high performance. And we want to also enable a future where we have more personalized medicine. We want to have devices, as I mentioned, that enables us to actually make decisions on our own. And we want to really understand more about life in general. This is comparative genomics, and you can see the complexity of the problem. You're comparing many, many genomes over here. And new genome sequencing technologies actually enable a lot of this. This is a genome sequencing technology called nanopore sequencing, which you can actually do with a device that looks like this. And this way you can actually personalize a lot of things. And again, I'm happy to talk about this, but we don't have time to go into detail of this technology. But these devices already enable you a future that can be personalized, but we need a lot more efficiency in hardware as well as software, in algorithms and the entire systems we design to make things more personalized and private, as well as high performance and efficient. And we need this in every aspect of our life. We want privacy, security, and personalization in health, medicine, devices we use, robotics, spaces. Because if you want a robot, for example, you want that to be customized for you. You don't want that to be customized for a random person that is not representative of you, right? And that's true for, I think, architectures as well, real architectures. Okay, so basically, this was a preliminary part of the lecture still. This lecture is really about questioning what limits us in designing the best computing architectures for the future. I will hopefully provide directions for fundamentally better architectures and designs, and I will advocate principled approaches. And let's see how much we can cover, of course. And one thing that's important to notice is that applications are increasingly demanding today because people are dreaming and applications are coming, meaning you can never, people's creativity is good enough to create new applications going into the future. Genomics is one example, for example, but there may be many, many other applications. And as applications push the boundaries and become more sophisticated, computing platforms and hardware will become increasingly strained. So we really need to rethink how we design the hardware and the software together. So in all of this, in everything I will talk about, a key realization will dominate. And that realization is that modern systems are bottlenecked by data storage and movement, essentially memory. So our focus will be on data storage systems because processing is relatively easy today. That's a general overstatement, of course. Memory is harder today, and there's a lot more opportunity to improve the memory system. So if you look at a system that it consists of processors, main memory, and storage, I think of main memory and storage as part of the same system. And it's a critical component of all computing systems, server, mobile, embedded desktop, sensor, whatever you're designing, you need to have some sort of working memory. And this main memory system must scale in many, many dimensions in terms of its capacity, technology, efficiency, cost, and algorithms we use to manage it to maintain the performance growth and technology scaling benefits that we've been used to. And again, you may attach to it processors, you may attach to it FPGAs, reconfigurable architectures, you may attach to it GPUs, you may attach to it machine learning accelerators, vision accelerators, a combination of all of those. In the end, all of them are bottlenecked by memory. And the reason is computing today is bottlenecked by data. All applications that are really interesting are data intensive, AI, ML, genomics. They require rapid and efficient processing of large amounts of data, and data is increasing. Basically, today we can generate much, much more data than we can process efficiently. And these are some example workloads that are pushing the limits. This is, of course, a sampling. There are more workloads, but databases, graph processing engines, data analytics engine, data center workloads, they're all bottlenecked by memory today. And also on the mobile end, web browsing, video playback and capture, and machine learning frameworks, for example, they're all bottlenecked by memory again. Genome analysis, as I said, today we have very good devices that can sequence genomes, but we're bottlenecked by memory in terms of our analysis. And as a result, our scientific discoveries and health applications are bottlenecked by memory today. As I said, this device, for example, is very good at sequencing your genome. You can actually buy this device for a relatively small amount of money, but you will be bottlenecked by memory when you're processing the data that comes out of it. So memory is really critical for performance today, but it's also critical for energy. I'm going to talk about this paper a little bit more, but this is a paper that we did with Google a few years ago in 2018, as you can see. We spent some time at Google to analyze their workloads, important workloads I showed you earlier, like machine learning frameworks, video processing, capture, and video transmission, streaming, for example, like what we're doing right now. And we found out that more than 60% of the entire system energy in mobile systems is spent on data movement across the devices. So this is a lot, basically. Today, we're wasting a lot of energy just to move data. And this is because of the way we design systems, as we will see. And in my opinion, we're designing systems in the wrong ways, that those wrong ways are resulting in this problem. If you actually design systems in fundamentally better ways, we can fix this problem, as we showed in our paper also. Memory is also critical for reliability. This is a study that we did with Facebook in 2015, as you can see over here. What we did over here is we studied all of the memory errors that happen in Facebook's data center. So Facebook has a lot of computers, actually. Probably some of you are using Facebook. Be careful about your privacy, but you're using it fine. So basically, you get failures all over the servers. And we wanted to understand how memory affects these failures. And basically, we found out that if the memory chip that's employed in a data center server is higher density, then it leads to more failures. And you can see this correlation in this graph over here. This chip density on the x-axis and for server failure rate, relative normalized here on the y-axis. And you can see that the chip density correlates with the server failure rate, meaning if a server that has a higher density chip that can store more data is more likely to fail. And the intuition is that as memory capacity increases, system reliability reduces. And this is because memory cells become less reliable as memory capacity increases because cells become closer to each other. So this is a big reliability problem, as you can see, going into the future. And I will give you more examples of this reliability problem in a little bit. So rewording my realization earlier, modern systems are really bottlenecked by memory and storage today, but storage is part of memory. Okay, with that, let me jump into some key issues and future platforms from the perspective of memory. I intend to talk about security, reliability, and safety, and talk about these fundamentally secure, reliable, and safe architectures, and talk about some really, really exciting and interesting issues in memory. And then I will switch gears and talk about fundamentally energy efficient architectures, how to get rid of the waste in terms of energy in computing architectures today. I will not have time to talk about this last two. Unfortunately, I have slides, but if people have questions at the end, I'm happy to try to cover. And I'm not sure if we are even going to cover both of these in full, because we don't have a lot of time. And Ahmet will tell me, hopefully, when we're close to running out of time. Does it sound good?
Yes, yes.
Okay, great. So I will continue then. Okay, so let's start with the first one, security, reliability, and safety. And I think this is a slide that kind of answers the question Ahmed asked earlier. So I learned about Abraham Maslow, who is a very famous psychologist in the 20th century in my psychology classes. And Maslow actually is a very dedicated psychologist. He dedicated his life to understanding why human beings do the things they do. So he really dedicated his life to understanding the theory of human motivation, let's say. And you can see that he wrote books about it, articles about it, etc. So why am I putting this slide? Maslow is more famous perhaps for this hierarchy of needs. He invented this hierarchy of needs, and he basically said the most important needs that we have are physiological and safety. Before we can satisfy those needs, we don't really care about, for example, love, esteem, or highest forms of abstract art. First, we need to be secure, basically, he's saying. That's why I think this is a good analogy for computers also. If our computers are not secure and reliable and dependable, maybe we don't really care about their performance, right? You get into a self-driving car and it malfunctions. It can kill someone or you get killed. Not a good idea, right? Then you don't care how fast it goes, right? Because you don't want to go into that car to begin with. So that's why this bridge is so important, because this bridge is an example infrastructure that has to be secure, reliable, and safe. And if it is not, it causes problems like this, which can be fatal. And I think, as I mentioned earlier, computers are even more important than bridges today in our lives. We rely on computers on all aspects, critical aspects of our lives, our health, medical systems, self-driving cars, etc. And they all need to be secure, reliable, and safe. And as I mentioned earlier, we want them to be extremely reliable like a rod, but we don't also want any bit flips in this rod. I say bit flips because I'm going to talk about bit flips that lead to problems in memory. So the problem I see is that we do not seem to have design principles for guaranteeing reliability and security today. And I'm going to give you some examples from it. As I mentioned earlier, as memory scales into bigger capacities, it becomes unreliable, right? And this is because cells are closer to each other, and there are many, many more cells, and cells are smaller. So as you pack more density into a memory chip, you need to put more cells into the chip, obviously, and you need to make the cells smaller also. That's how technology scaling works. And both of them are not good for reliability and security and safety, as we will see. This is also called the memory scaling problem, or the DRAM scaling problem. Now I'll go into a little bit more detail. If you've taken a course in electrical engineering, you may have seen a circuit that looks like this. This is called dynamic random access memory. You store data in this capacitor, and you access data using this access transistor. And you store data in terms of charge in this capacitor. It's charge-based memory, as you can see. And for this memory to work, the capacitor must work. It must be large enough for reliable sensing. And the access transistor must work. It must be large enough for long data retention time. The data should not leak through this resistance capacitance path through the word line and the bit line, as you can see. Now, the problem is, as we reduce the size of a cell so that we can put more capacity, so that we can deal with a lot of data, the cell becomes smaller. It becomes more vulnerable. It becomes more vulnerable to noise from the environment. And we wanted to study these effects. So basically what I showed you earlier with Facebook is a study of these effects in a large scale. But we also wanted to study these effects on real chips in a controlled manner. That's why we built these infrastructures. These are hardware FPGA-based, reconfigurable logic-based infrastructure. You can see the Xilinx boards, for example, where we can actually test memories. We can test many, many aspects of memory, as you can see from these papers. I'm not going to talk about all of those papers, but this is one example of our infrastructure. We can do many FPGAs, parallel testing of many different memory chips to understand their characteristics, reliability characteristics, and performance characteristics. And we recently open sourced our infrastructure. If you're interested, you can read this paper. And it's also open source on our GitHub. You can program this using C++, so it's a high-level abstraction. And you can do this testing using C++. So you don't need to deal with a low-level Verilog code, for example. And people are using it actually to improve research all over the world. And this is the paper that they're building on. So while we were doing these studies, we discovered something very, very interesting. And this is basically, we discovered that you can predictably induce errors in most DRAM memory chips. This should not happen, basically. You should not be able to do something to the chip and cause errors by just writing or reading in software, right? Of course, if you go to the chip and if you make it really warm, hot, for example, beyond the temperature that it's supposed to operate at, then you can induce errors, fine. But that requires physical access. But we found out that you can predictably induce errors using purely software. So this is now known as the Dm Ropehammer problem. I'm going to talk a little bit more about this. It's essentially a simple hardware failure mechanism that can create a very widespread system security vulnerability. And people are writing articles like this. So this is Wired magazine. You may be familiar with it. And they basically wrote an article saying, forget software. Now hackers are exploiting physics. And this is a very good high-level characterization of RowHammer. Now, let me tell you what the problem is at a low level. So memory consists of rows of cells. Each cell is 1 bit. Each row is 8 kilobytes or something like that, for example. So if you want to access some cells in a row, you apply high voltage to that row. This is called an activate in DRAM. Now, if you want to access something else, you deactivate this row, meaning apply low voltage to that row. This is called precharge in DRAM. Now, if you keep doing this repeatedly, let's say, apply high voltage, low voltage, high voltage, low voltage, activate, precharge, activate, precharge, activate, precharge, activate, precharge, activate, precharge, enough times before the cells get refreshed in DRAM, it turns out you get errors, bit flips in adjacent, physically adjacent rows in vulnerable cells. Now, this is not supposed to happen. Basically, you stored some data here in the adjacent row. It was a 1. It became a 0 after you did this row hammering, let's say, activate, precharge, activate, precharge, activate, precharge, activate, precharge. Clearly, that's not supposed to happen because you're not even touching this row, right? And this is bad, basically. You're just reading this row and causing errors in other rows. We call this a hammered row, and we call these the victim rows. And we basically showed between 2012 and 2013 that more than 80% of all of the chips that we tested from 3 major memory manufacturers, there are only 3 major memory manufacturers in the world today, are vulnerable to this problem. So they're all problematic, basically. And this is a scaling problem because recent DRAM, recent memory modules are more vulnerable. As you can see in this graph, we tested modules from 2008 to 2014 at the time, and we plot the error rate over here. And you can see that older modules did not have this problem, but newer modules that were manufactured in 2010 had this problem because cells are closer to each other, right? And all modules that we tested that were manufactured between 2012 and 2013 actually had this problem because cells are definitely close to each other, and because of the noise effects, because of the electromagnetic coupling, when you actually do this row hammering, activate, precharge, activate, precharge, activate, precharge, you're causing more perturbation and disturbance to the adjacent cells, which you couldn't have before in 2008 because the cells were far away from each other in 2008. As technology scales, cells become closer and they start affecting each other more. That's why this is a technology scaling problem. And in the future, this problem will get worse, as I will show you later on. Okay, so why is this happening? I think I already said this, but cells are too close to each other. As a result, they're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells and wires used for accessing the cells. This is also called cell-to-cell coupling or interference. So when we activate, for example, apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer happens enough times, charge in such cells get drained before the cells get refreshed. And this simple circuit level failure mechanism has enormous implications on upper layers of the transformation hierarchy. Basically, users get affected by this. And some people may be hacking computers because they take advantage of this. So the reason is a simple software program, user level program, can induce these bit flips. So you look at this program. At the time we released our code, you can see that our code is very simple. It selects address X and Y, they map such that they map to rows that are close by. And it basically ensures that you don't need to understand the code. Basically, what this code does is this. It basically ensures that you keep activating X and Y continuously until maybe you get bit flips in adjacent rows. And we showed that Intel and AMD systems at the time are vulnerable, but there's nothing fundamental about Intel and AMD. As long as you have a system that has a good enough memory controller that keeps accessing memory like this, you can actually cause errors. And we showed that later on. Other people showed that later on. So this is a real reliability and security issue. And when we wrote the paper in 2014 in ISCA, we basically said memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I strongly believe this. And we basically said someone can hijack your computer by taking advantage of these bit flips so that they become, they take over your system completely. And while we were working on this, good folks from Google Project Zero did exactly that. They published this beautiful blog post, which I encourage everyone to read if you're interested in security engineering. They basically said they did that. So this is a copy and paste from their blog post. They basically said they learned about the problem from our paper. They replicated the problem on their own systems. And they basically built 2 attacks, security attacks. One attack is very interesting. It uses RowHammer-induced bit flips to gain kernel privileges on a Linux system when you run the program as a user-level process that has no privilege. Basically, there are no bugs in the system. You just cause RowHammer bit flips and get access to the system completely. And the way they were able to do this is very sophisticated. I'm not going to go into detail, but I'll give you the key idea because I think it's very creative. And it's a very good example of security engineering I would recommend people to look at if they're interested in this. Basically, they were able to induce bit flips in the page table entries of the program that's doing this row hammering. And they were carefully able to induce bit flips such that the process gains write access to its own page table, such that they can circumvent all of the memory protection that the operating systems provide today. So if you gain write access to your own page table as a user level process, you can modify anything you want in the system and access anything you want in the system. And once you access anything you want, essentially you've circumvented any sort of safety, security protection, and also privacy protection that exists in modern systems. So this is beautiful, and I would recommend you take a look at it. Later, this became famous as the Dm Ropehammer Vulnerability, and people start drawing pictures like this. And a very famous hacker on the internet, they wrote that Ropehammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. And this is a very nice, I think, overall description of Ropehammer. Okay, let me give you a quick history of what people have done. Security community actually did a lot of really interesting work. These folks basically show that by using RowHammer, they can gain unrestricted access to systems of website visitors by taking advantage of RowHammer in JavaScript. And you can read this paper if you're interested, or watch the talk online. These folks show that they can gain control of a smartphone deterministically completely. Very interesting. An Android phone, for example, you can download this application perhaps even right now. These folks show that you could do this much more efficiently in GPUs so that you can actually do RowHammer much faster. These folks show that you could do it over the network through the remote direct memory access protocol. And these folks show essentially the same thing. So you don't have to have any access to the system to be able to do this. You can do it over the network also, as you can see. These folks show that even if you cannot take over the system, you can gain private information, access private information. And more recently, these folks show that you may have a very good network, neural network, that is trained to do accurate prediction, but actually by doing RowHammer attacks, it becomes completely inaccurate. So this is more interesting over here, perhaps. This was published last year, for example, as you can see. Before the attack, before RowHammer, the accuracy was quite good. They were able to do prediction with 90% accuracy, for example. For example, if you're doing a self-driving car, if you want to predict, oh, am I close to a pedestrian? Let's say 90% of the time they're accurate. Ideally, you would like to be 100%, of course, right? But if you actually are under attack, and somebody is executing a RowHammer attack on you, the accuracy becomes 10%. So essentially, the neural network becomes completely useless if you're attacked with the simple RowHammer attack. That's why these security and safety issues are extremely important, in my opinion. All of the other advances that happen in computer science and engineering today, in artificial intelligence, machine learning, they're all very interesting, but they all depend on the fact that we can design safe and secure systems that do not cause these attacks. Okay, there are more works, but I'm not going to talk about it. I will make a joke that maybe this person is trying to solve the RowHammer problem by hammering their computer with a real hammer. But of course, this is not a good solution, right? So let me talk about solutions quickly. So this is Apple's patch for RowHammer. When Apple actually released their patch for RowHammer, they basically said they increased the memory refresh rates. So clearly, this is one solution, but this is a solution that we have today because we don't have anything else. And this is not a good solution because this increases your energy and power consumption. So you don't really want to do that. This is done because we don't have intelligent memory controllers today, which is the topic of the next part of the talk. And I like Apple because Apple actually cited our work in their security release, saying that it was really inspired by this work, the solution. Okay, so I think the real solution direction is really building principal designs. We want to design fundamentally secure computing architectures, and we would like to be able to predict and prevent such safety issues, in my opinion. So our solution is more intelligent. Very quickly, we basically do probabilistic adjacent row activation. So after closing a row, memory controller activates one of the rows with a very low probability. And this probabilistic solution actually gives you a very good reliability guarantee. And you can actually adjust the value of the probability to increase the strength of protection if you want. And I'm not going to go through the advances in detail, but this is low power, low overhead, as you can see. It's stateless. It's an effective solution. And today, actually, versions of it are implemented in the DRAM chip and the memory controller. I'm not going to talk about this in detail because I think the implementations are not great. The way we implemented it, I think the vision was good, but I think the implementations need to be more refined going into the future. But I will say that this solution, a version of the solution, was implemented by Intel in their memory controllers. You can see this is the BIOS of an Intel computer. You can either pick your hardware RowHammer protection as your RowHammer solution, or you could double your refresh rate. And you could pick the probability of activation of the rows, similar to what we described, but it's a little bit different. But it's inspired by our solution, as you can see over here. Okay, I'm not going to talk about RowHammer in more detail. If you're really interested in the solutions, we talk a lot more about solutions in my lectures, for example. And this is our first RowHammer analysis. I'm going to tell you a little bit more about RowHammer, and then we're going to conclude the first part of the talk. So if you want to really know about this more, we recently wrote a very long paper that talks about, invited paper that talks about a lot of issues related to RowHammer, covering security, software, systems, architecture, logic, circuits, and devices. So let me talk about some exciting work in 2020 that has been done that shows that the problem is continuing. So this is a work that we published in 2020, and we basically studied more than 1,500 memory chips, and we basically showed that RowHammer problem is getting worse. Chips are becoming more vulnerable, and today you can actually do 4,800 hammers to cause a bit flip, and chips in new technology nodes actually are more vulnerable. And unfortunately, existing mitigation mechanisms are not effective. We also showed in this work which was published in Security and Privacy, as you can see in IEEE top conference on security and privacy. We basically showed that DRAM manufacturers, after we did our work in 2014, DRAM manufacturers said we solved the problem. So they basically released chips into the market saying that, oh, the problem is solved, these are RowHammer free. But we basically didn't believe it. We questioned that assumption. This is, I think, very important for critical thinking. If somebody claims something and says something, you don't necessarily trust it, right? If they don't provide a proof, of course. So you basically do your own investigation. And with our own investigation, we found out that that's not true. But that's not true because they designed mechanisms inside the chips to protect. That's correct. But they were not good enough. So we basically reverse engineered some of those mechanisms and showed that you could circumvent the protections that DRAM manufacturers put in their chips. And the chips are vulnerable to RowHammer, again, if you circumvent them this way. So if you're interested, you can read this paper or watch my lectures, as I mentioned. And it's fascinating, I think, but I don't have time to talk about this in detail because there are a lot of interesting stories here, clearly. And we also did some work with Microsoft, as you can see, on trying to answer the question, can we somehow identify chips that are not vulnerable to RowHammer? And this is a very difficult question, actually. And in HPCA, we recently proposed a solution, described a solution called BlockHammer, and this is already online, so you can watch the video that Giray delivered. So if you're interested in RowHammer, we have a lot of detailed lectures online, as you can see. And also, I recently delivered another lecture, The Story of RowHammer, which covers a lot of the things that I just discussed. Okay, so let me talk a little bit about the future of memory reliability and security and safety. So unfortunately, systems and memory in particular are becoming less reliable and more vulnerable. This is not just memory, actually. Computing, all of the computing devices are all becoming less reliable. But due to difficulties in memory scaling, other problems may also appear, or they may be going unnoticed. Some errors may already be slipping into the field. And RowHammer is one example, but there could be retention errors, read errors, write errors, etc. And those errors may also pose security vulnerability. So, and you don't know if people are exploiting the security vulnerabilities actually until you publish them and make people aware of them and try to fix them. Some people may already be exploiting these security vulnerabilities. You don't know necessarily. And all memory technologies are vulnerable, actually. DRAM, flash memory, emerging technologies, which we do work on, they're all vulnerable to this problem. So this is our three-step methodology that we're working on to keep memory and systems secure. We would like to understand, architect, and carefully design and test. So understanding requires developing methodologies for failure modeling and discovery. Architecting requires principled architecting of system and memory. And design and test requires principled designs, automation, and testing. I'm not going to go into the details, but we do work in all of these areas. So that's why we develop our infrastructures that look like this. We also have an infrastructure for SSDs, solid-state drives, flash memory. And we actually have written papers on understanding flash memory reliability. If people are really interested in what goes on in your solid-state drives, for example, I would recommend you take a look at this invited paper that we wrote to proceedings of the IEEE, as you can see over here. Okay, before we conclude this reliability, safety, secure direction, I think there are two other solution directions. One is looking at new technologies that do not have this problem. I think it's difficult because I think all technologies have this problem, but some technologies may have less problem than DRAM. Non-volatile memories are one example, and they also provide other opportunities. And the second direction is embracing unreliability. Design memories with different reliabilities and store data intelligently across them. For example, you don't store your security critical data. You store, most of your memory is not reliable, for example. A small chunk of your memory is very reliable, and you store your security critical data into your reliable memory. So that's one other approach. But of course, this requires some system-wide design. Essentially, fundamental solutions to security require co-design, hardware, software, co-design across the hierarchy, similarly to the axiom that I mentioned earlier. It spans across the stack, basically. So this is the end of the RowHammer, or fundamentally secure, reliable, and safe computing architectures direction. And I think the takeaway is we want intelligent controllers to solve these problems, and hardware, software, co-design as well. So this brings me to the second direction, but I'm happy to take questions at this point if people are having questions related to RowHammer and security and reliability. Any questions? Should I keep going then, since I don't hear anything?
Yeah, we can keep going, and I want to remind you, we can finish this part 20 or 25 minutes.
Okay, 20, that should be possible. I have more material, but I don't need to talk longer. Okay, so let's talk about this part, and then hopefully there'll be more questions at the end. And feel free to ask any question. I'm open to answering. So this part is also very important, I think. As I said, security is the first step, but energy efficiency is also extremely important, right? We really want efficient systems going into the future. And again, I will use Maslow as an example. And when Maslow put his hierarchy up, he didn't say security is the most important thing. If you look at the bottom of the hierarchy, physiological needs are much more important, right? And you could say energy is much more important than security, arguably, right? Because if you don't have energy to do any computation, who cares about your security and safety? You're not going to be able to do anything anyways, right? And that's, of course, a joke. I think these are fundamentally important, both of them, but energy is really critically important. And as I said, do we want a future that looks like this, sustainable, energy efficient? Or do we want a future that looks like this, very bad for future generations? I would argue we want the best of both worlds. We want high performance, high productivity, but we also want it at energy efficient and sustainable ways. And I think this is really, really important, especially today when we have huge problems with climate, and computing systems actually consume a large chunk of the power in entire systems. And the power of the computing system is actually growing as a fraction of the power that's used in the entire world. In fact, I think data centers are using maybe 3 to 4% of the entire world's power today, which is fascinating because these are data centers only, right? So I think we need to do something about it. So the problem today is data access is the major performance energy bottleneck, but current design principles we use to design computers with cause great energy waste, and they also cause great performance loss. And let me give you examples of this. I will get to the heart of the problem. Basically, today, processing of data is performed far away from the data. As a result, we move data a lot. That causes performance problems. That causes energy problems. To tolerate the performance loss, we add a lot of complexity to our systems, to our software and hardware. We add a lot of mechanisms to basically try to tolerate these things, add buffering, add out-of-order execution, add multi-threading, add many latency tolerance mechanisms, prefetching mechanisms, caching mechanisms, both in software and hardware. So systems becomes very, very complex. As a result, they waste even more energy. So today we're in a vicious cycle where we're trying to fix the performance problems of processing data far away from the data, but we're causing even more problems. So if you look at a computing system, it consists of communication, computation, and storage devices. We've heavily optimized the computing systems today, and they're overwhelmingly processor-centric. So basically, everything needs to go to the computing units so that you can do operations. You cannot do operations inside the memory or storage unit, for example. And this comes at a great system cost. Processor is heavily optimized and is considered the master, and everything else is dumb and largely unoptimized. Yet we know that we should do something better. So this is a quote from Dick Seitz, who was the chief architect of Alpha processors in 1990s, which was the fastest processors of its time. And he basically said, it's all about memory. His team designed this really fast processor, fastest processor of its time in 1990s. After that, he wrote this one-page article in Microprocessor Report saying that we designed this processor. It's capable of finishing 4 instructions every clock cycle, but it's finishing 1 instruction every 4 to 5 clock cycles. Basically, it's operating at 1/16th to 1/20th of its bandwidth. That's 5%, let's say. Why? Because it's waiting for data to come back from memory. It's unfortunate. And he finished the paper saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I think this is very telling, and I would recommend you take a look at that single-page paper that we link from my course websites, for example. Okay, fast forward about 10 years. This is data from my own PhD thesis, my first paper. We collaborated with Intel. We analyzed all of the workloads that they used to design their processors with. And we basically found out the same thing. On these important workloads, the processor is waiting for data to come back from memory for more than 50% of its time. Okay? That's not good, right? And if you're interested, this is the paper that I wrote. This is the first paper that I wrote, and you can take a look at it. Okay, maybe you don't believe me or you don't believe Dick Seitz. Since everybody believes Google today for some reason, I don't know why, I would suggest not believing anyone without questioning. In general, critical thinking is extremely important, especially with the scientific mentality. You cannot believe anything without questioning, right, and verifying. But basically, Google did essentially the same thing. They examined all of their workloads, data center workloads, according to them. And they basically showed that most of the time, the processor is waiting for memory. Only 10 to 20% of the time, the processor is processing instructions. And they have more analysis, and I would recommend you take a look at the paper. That's beautiful. So basically, today's designs are processor-centric. You need to move the data to the processor to process it. You cannot do operations inside the memory. This leads to a grossly imbalanced system. Processing is done only in one place, and everything else just stores and moves data. As a result, data moves a lot in the system. It's energy inefficient, low performance, and complex. And also, to tolerate the data movement, we design overly complex and bloated processors and accelerators and software as well. This leads to complex hierarchies and mechanisms. It's energy inefficient, low performance, and complex, especially when it doesn't work, right? We do all of this caching, for example. If it doesn't work, you lose performance and you lose energy as well. So basically, we have a picture that looks like this. This is my cartoonish picture, but most of the system is dedicated to storing and moving data. If you look at a processor, most of the processor is really consisting of caching, interconnects, other caching, memory control, other caching, memory, and storage, and other interconnect structures, data storage and movement, basically. More than 95% of the hardware real estate of the system is dedicated to data movement and storage. So let's look at the system level perspective of this. Essentially, as I said, data access is a major bottleneck. And as I already said earlier, applications are increasingly data hungry. Energy consumption is a big problem today. And data movement energy dominates computation energy today. That's especially true for off-chip to on-chip data movement. Let me give you an example that compares data movement energy to computation energy. And this is a slide that I borrowed from Bill Daly. This is relatively old numbers, but the general idea holds. The numbers have changed, of course, over time. But let's take a look at an arithmetic operation today. This is a complicated arithmetic operation, 64-bit, double precision floating point operation. It consumes 20 picojoules. And memory access is 16 nanojoules. That's 800 times higher than the computation. So today, computation is cheap. It's nothing. It's not expensive. So a memory access today is about 2 to 3 orders of magnitude more costly in terms of energy than a complex addition. And this is this way because memory is hard to improve because it consists of these interconnects that do not scale well with technology scaling, whereas computation is done using logic gates. And logic gates have scaled really well, became smaller and smaller and much more energy efficient over 70 years of technology scaling, whereas memory did not scale very well. As a result, we have this really bad picture. So imagine you're adding 2 numbers, add A to B and store the value in C. You need to fetch those numbers from memory, and you need to write the result back to memory. That's 3 memory accesses just to do a very simple addition. It's even less, it's even cheaper than this double precision floating point operation. So you're basically consuming 3 times, 3 orders of magnitude more energy just to do a very simple addition, right? That doesn't sound good. Okay, so there are other papers that talk about this problem, and you can see that different costs have been put out. And as a result, we see the results that I mentioned to you earlier in our collaborative work with Google. Most of the system energy is spent on data moments in existing systems today. So basically, I will argue that we do not want to move data at all. We want to keep the data where it is, and we want to do computation at that place. So to be able to do this, we need a paradigm shift. We need to really enable computation with a minimal data moment. We need to compute where it makes sense, where data resides. It could be in storage. It could be in memory. It could be in caches, wherever data resides. And we want to make computing architectures data-centric. And this is a paradigm shift today. So let's take a look at the case of memory. So memory is important because it can store a lot of data. So we're going to store very important things in memory, databases, graphs, media, whatever application that's interesting. Machine learning could be another thing. And we're going to ask memory, can you do this computation for me? And the memory is going to say yes, and memory is going to provide results. So there are many questions over here. I'm not going to cover all of them, but I'm going to give you the high-level questions. I think this is a very fascinating research area. How do you design the compute-capable memory and the controllers? How do you design the processor chip and memory units in a system like this? How do you design the software and hardware interfaces? How do you do the programming? How do you design the system software, compilers, and languages? How do you design the algorithms and theoretical foundations of computing to be able to achieve this? Again, this is a problem that spans across the stack, algorithms to devices, even theory of computation. If some of you have studied theory of computation, today we count operations to designate the complexity of algorithms, right? But that's not a good way, because that doesn't take into account the memory bottleneck, which is the much more important thing today. So maybe we really need to rethink the fundamentals of computing today. So let me start in terms of how we can actually achieve this. I'm going to give you some quick examples, not too much detailed, hopefully, but I'm going to give you examples that can give a lot of benefits. So for example, I'll start simple. I'm going to talk about data copy and initialization. And copying large amounts of data, initializing large amounts of data is done in many, many applications by operating systems, by virtual machines, by, again, operating systems or programming languages, etc. And in the paper that I showed you earlier from Google, they basically said only 2 function calls consume about 5% of the cycles, execution cycles in Google's data center. This is a lot for just 2 function calls. And it's not the entire data moment, as you can see. So how do we do the bulk data copy today? Today, we go through the processor, unfortunately. Basically, if you want to copy the source page, white one, to this gray one, you have to go through the processor. You bring the data all the way into the L1 cache. You bring the destination all the way into the L1 cache, do the copy, and write back the data. Now, this is high latency because you need to move data a lot. This caused a lot of bandwidth utilization in the most important bandwidth bottleneck resource in the system. This caused cache pollution, and this caused unwanted data moment because you may not actually want to reuse this data overall. And with a small page copy through the direct memory access engine going through the memory controller, not the caches, it basically takes about 1,000 nanoseconds today and 3.6 microjoules. Now, if you show this picture to a child who can think critically, and if you ask him or her the question, is this a good idea? Maybe they will tell you, no. Why don't you just do this inside the memory and don't bother anything else in the system? And that's how we need to think today, I think. Think critical and think like a child, maybe. Think simple, essentially. And the idea is we don't go through the processor. We do it inside the memory, this low latency, low bandwidth, no cache pollution, and no unwanted data moment. So I'm going to show you a mechanism that takes this 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules in an unoptimized way. Okay, so hopefully this is clear. And the idea is very simple after that. We call it row clone. And inside DRAM, there are a bunch of mechanisms. I'm going to show you the simplest mechanism. If you have, you remember this rows in DRAM, you have a bunch of rows inside DRAM. It's called the DRAM subarray. And to be able to read the data, you need to bring it into the row buffer, for example. So we're going to take advantage of this operation. We basically first activate the source row, which brings the data into the row buffer. And then we're going to activate the destination row immediately, which will implicitly deactivate the source row, and then copy the data from the row buffer into the destination row. So basically, by using the internal structures in DRAM to do the copying, intermediate copying, we can actually speed up the copy operation significantly by just doing 2 consecutive activates, not bringing anything into the processor. So this all happens inside the memory chip. Data doesn't move outside the memory chip. It doesn't go into the processor. And the hardware cost is really negligible for this. But the benefit is very high. Ignore these 2 bars over here, but this is baseline, the blue one. The red one is what we get. So the latency reduces by an order of magnitude, and energy reduces by if you really optimize that, actually close to 2 orders of magnitude, but it's more than 70x. Ignore these 2 things because they depend on where the data is, but we have developed better solutions to it in later papers, and they're much more similar to this red bar today, basically. Okay, so if you're interested, you can read the papers, of course, but the thinking here is that memory is an accelerator. So we are designing all of these accelerators, CPUs, GPUs, video processing engines, machine learning engines, vision processing engines, etc., audio processing, speech processing, etc. They're all accelerators. They're good. We know how to design them, but they're sitting on the wrong side of the memory bus. We need to put some accelerators that are sitting on the right side of the memory bus, such that they can act on data immediately, and they don't need to move data. They're not bottlenecked by this memory bus. So basically, memory is similar to a conventional accelerator, and we're going to design this computation capability such that the memory does things that it's really, really, really good at. Okay, so similarly, we can support in DRAM and, or, and not at low cost using analog computation capability of DRAM. And I'm not going to go into a lot of detail over here, but activating multiple rows concurrently performs computation, and you get 30 to 60x, 60 times performance energy improvement. And you can read the paper for more detail. And similarly, new memory technologies enable even more opportunities because they're non-volatile. I listed a bunch of these technologies over here. Phase change memory is something that we have worked on for more than a decade, for example. You can operate on them with minimal data movements, and you can actually do matrix multiplication using analog computation in some of these technologies based. I'm not going to talk about these in detail. And again, I'm not going to go into details of how we exactly do it, but let me give you some results. This is from real database called Bitweaving database. And we ported that application to our simulator that can do these in-memory computation operations. And we essentially observe more than an order of magnitude latency reduction in database queries. You can see 4 to 12x. So this is very significant, as you can see. And if you're interested, you can read the papers that we have written on the topic. We have also looked at other interesting applications like graph processing. Graph analytics is everywhere today. Bioinformatics actually uses a lot of graph processing. A lot of machine learning frameworks are based on graphs today. And graph computing is very fundamental. And large-scale graph processing is challenging because it's really memory bound. If you can add a lot of cores to the problem, but the cores will be idle. They will basically waste your energy. So fundamentally, graph processing is bottlenecked by memory because you do frequent random memory accesses and little amount of computation. So you're really exacerbating the memory bottleneck. So to be able to tackle this, we use 3D stacked logic and memory technologies. Let me quickly introduce you to what these are. You have memory in the blue layers, you have logic in the yellow layers, and you 3D stacked both these chips. So they're not 2-dimensional, they're 3-dimensional. So you can keep adding memory, and hopefully in the future, you can keep adding logic also. And there are real examples of this. The logic is connected with high bandwidth, low latency connections at low energy to memory layers. And other 2 3-dimensional technologies are under development by researchers. And this is how we use it in our system level graph processing engine called Tesseract. I'm going to briefly talk about this. Basically, we have this memory and logic. And internally in the logic layer, we have a bunch of processors. These in-order cores are processors. And these processors can operate on the data on top of them. And if you want to actually execute some application, if you want to update a location, you don't move the data to the processor that needs it, but you actually move the function to do the update to the processor that houses the data. Okay, so basically here the idea is you don't move the data, you move the computation to the data. And to be able to do that, you need to have some interconnection inside the logic layer. And then to be able to scale up the system, you need to have many of these memory plus logic chips, let's say. And then you actually attach it like a GPU to a host processor. So you can do your acceleration in this processing in memory engine. Again, I'm not going to go into a lot of detail over here, but this is a near data processing engine where cores can do computation and data doesn't move. You move the functions to the data. So it's really remote function call based programming. It's similar to a distributed system today, how you distribute system programming is done. And we add actually prefetching mechanisms that are similar to graph processing operation that are basically based on graph analytics. Okay, so we evaluate, I'm going to give you some results so that you can see the benefits of this. So we evaluate some systems, as you can see, they all are bottlenecked by memory over here. Tesseract, a processing in memory system, doesn't look like existing systems. Why? Because processing and memory are tightly coupled. Here, you can clearly see the boundary between processor and memory. processors and memory. Processors and memory. Here, processors and memory are together. You cannot distinguish them, right? As a result, you get very high bandwidth available to the processors, 8 terabytes per second over here, as you can see. And you can see that the benefits are very high. This, through the algorithm architecture co-design that we have, you get 14x performance improvement across 5 graph processing algorithms. And actually, this is 2015, as you can see. Later work improved on our work and showed that you can get 2 orders of magnitude by designing the system much better with other ideas that they developed. So it's more than 100x today, actually. And I'm not going to go into more detail, but the energy also improves by close to an order of magnitude. And actually, the recent work showed that you could actually increase that to almost 2 orders of magnitude as well. Okay, so if you're interested, again, this is the paper that we wrote at the time we did the study. Let me quickly talk about mobile devices, and then we're going to get closer to the conclusion. This is work we have done with Google. I wanted to mention that because this is also important because mobile devices are everywhere, and energy consumption is really extremely important in them. And we wanted to understand the effect of data movement on energy in these workloads that everybody is using some examples of. And we basically found out that more than 60% of the energy is spent on data movement, as I said. And we wanted to understand whether you can actually improve that significantly by designing computation units inside the memory. And of course, there are challenges here. So we actually tackled a lot of these challenges in realistic ways in this work. And the second key observation that really helps us is a significant fraction of the data movement comes from simple functions. So if you understand your software really well, you can basically figure out what these functions are that are consuming a lot of data movement, and can offload those functions to main memory. And that's essentially what we did. And you can design some lightweight cores or specialized logic or reconfigurable logic near your memory to accelerate these applications. And overall, we found that you can improve performance energy by 2x. 2x is actually quite good, I think, for these because we're not changing the system much. We're basically saying, the applications are exactly the same as today. We just want to identify some functions that are really important in terms of data movement and offload them to processing engines inside memory. Okay, I'll quickly go over this. Basically, there are functions. So this is TensorFlow machine learning. Clearly, it's important, right? It's a neural network. And in neural networks, there are a bunch of functions like packing and unpacking and quantization that lead to a lot of data movement. And that's caused a lot of energy spent in the system. And we actually accelerate those functions so that we can get significant improvements, for example. So similar functions exist in other workloads as well, but machine learning is clearly important today. So if you're interested, you can look at this paper or my lectures also more detail. So we did a lot of, we're doing a lot of work in this area, and I'm really fascinated by this area because we want to really change the computing paradigm. I'm not going to go through and talk about these works. I'm just going to go over these slides so that we can get to the parts that we're really interested in at the end. So you can see that we're actually doing work on accelerating approximate string matching for genome analysis. If you're interested, you can also take a look at that. So I believe we need to revisit the entire stack to enable processing in memory, but we can get there step by step. And if you're really interested in this topic, we have recently written this overview paper that's really accessible, in my opinion, that talks about processing in memory. And it was written in December 2020, as you can see. And I would also recommend looking at some of our other papers. So the good thing today is there are real systems. So when we first started doing research in this area in 2011, 2012 or so, there were no systems. But now there are companies that are designing chips that can do processing inside memory. I'm not going to talk about this in detail, but we are actually working with them to understand the benefits and upsides and energy efficiency and performance of these systems. It's a startup that's in France that have put processing engines inside the chips of memory. Now, I don't have the slide, but recently Samsung last month announced that they also add simple computation capability in a similar way, in a very similar way actually to this UpMem. So Samsung is a huge memory company, if you don't know. And essentially, they basically said they also are putting processing in memory inside their chips in a very similar way to these guys from France, except they're more specialized for machine learning. Okay, so if you want to learn more about PIM, we have a lot of detailed lectures, again, from my course. And Juan covers UpMem in this lecture over here, if you're interested. And there's more, as you can see over here. And I give tutorials and talks on processing in memory in depth. And this was delivered in International Electron Devices meeting, which is really the major conference in device level conference that have introduced a lot of innovations to our computing systems. So you can take a look at that also. That's online, as you can see. So this was the second big challenge and opportunity for the future. How do we design fundamentally energy efficient and data-centric computing architectures? And I think if you want to be fundamentally energy efficient, you need to be data-centric. You should not move data. If you want to be high performance, you should also be data-centric. You should not move data. So I think high performance also goes along with this. As I said, I'm not going to cover these parts over here. Let me actually go to the slides at the end. Somehow I lost my sharing. I'm going to do that again. But I'm going to conclude basically. If there are any questions, I'm happy to answer them at this point.
Can I ask?
Yes, please, go ahead.
It's probably one of the most common and fundamental questions in computer architecture. I am wondering your thoughts.
Sure.
We are using binary size system. As far as I know, DNA, for example, much more memory efficient than our hardware systems.
Mm-hmm.
Is it possible to produce a system like DNA, which is using more than 2 variables? If it is possible, why we are not producing it?
Yeah, that's a very good question. So, okay, there are multiple answers to your question. First of all, today, so in flash memory, for example, SSDs, you can actually store more than 1 bit in a cell. You can actually store 4 bits, for example, or 8 bits in a single cell. So it's better than before, in the sense we're packing more information. But yes, it's not exactly like DNA today, right? DNA packs a lot more information into a very small amount of symbols, let's say. And I think people are working on this. This is actually an old idea. I think people started working on this in 1980s or so. Can you actually use DNA for storage in computational systems? There's been some progress, but unfortunately, it has not been good enough so far. Part of the reason why it has not been good enough is the reading process of the DNA is very, very slow and not so accurate. So you saw those devices, the sequencing devices, right? If you store data in DNA, you need to sequence the DNA first, and then figure out whether the bases are A, C, T, G, and then decode your information that you stored over there. And it turns out this sequencing process is very slow. The interpretation process is also slow, and it's error prone. And as a result, that's the major reason why it's not used today. In the future, who knows, right? Maybe 10 years, 20 years down the road, we will have DNA-based storage systems. But again, I think we need to be very careful in terms of where we can use them. In my opinion, DNA is very, very aggressive. And in a sense, the design point of DNA, it's really designed to store very long-term information for a really long time, right? And clearly, the reading process in our bodies are very different from the reading process that we use in systems today. So I think we need to improve the reading process going into the future. Somehow we need to learn from nature. I don't know how, but nature does a good job in replicating the DNA and figuring out the information. We're not as good today. That's why we want to do research, as I discussed, accelerating genome analysis. And that requires research. And the second part is we need to improve the speed of it. So for example, DRAM, we can read data within nanoseconds. Within today's DNA analysis systems, we can read data within a day. Okay, if you're really aggressive, you can parallelize it across a data center and do it maybe within hours. But again, we want to do it in nanoseconds if you want to do very fast computation, right? We don't want to wait for days or hours. And I think that latency problem is actually a very tough problem in terms of DNA type of storage mechanisms. But again, research is going on. I'm not sure how successful it will be down the years, but we will see. Now, there are other technologies that are also interesting. So people at Microsoft have been looking at storing information inside glass, for example. There's something called glass storage project. And I think that's also very interesting. And potentially more feasible, let's say, in my opinion, at least from what I've seen based on the publications, scientific publications. So storing data inside glass and reading data from glass could be interesting as well. Maybe the density is not going to be as good as DNA, but the latency and accuracy characteristics may be much better than DNA. And then there are also other technologies like phase change memory, where you can actually store data in terms of voltage levels, in terms of analog information, that is better than a single bit per cell again. So there's a wide spectrum of memory devices, and I think they all come with different characteristics. And I think it's a fascinating area to do research on, and we will see how it pans out. Hopefully that answered your question.
Yes, yes, it is. By the way, we are out of time.
Okay.
But you can shortly conclude, I think. And we can.
I have a question, please.
Okay.
Yeah, I'm happy to take questions. I think if
Okay.
there are questions, I will prioritize the questions.
I'm a freshman and I'm naive. I don't have much knowledge, but I just wanted to ask this question about the RowHammer. I wanted to know, does each row or cell in the memory have its own capacitor?
So basically, if you look at each row consists of many capacitors. So a row has 8 kilobytes, let's say. That's 64,000 capacitors connected to each other via word line. Does that make sense?
Yeah, okay. So this brings me to my second question. So if each row has so many capacitors, so I think can these capacitors in each cell be connected or channeled so that when the memory is accessed in one cell, the channel or connection breaks to prevent the effect on that cell from spreading to the adjacent cells as a result of discharging in each cell?
Yeah, I think I can see maybe where you're going at. It's very difficult to do, basically. I think certainly, basically, I think maybe you're thinking you can somehow have a connection, let's say, to a capacitor that tells you that something bad is going on, right? Let's say.
Yeah.
And if you do that, yes, I think actually there have been proposals like that that basically try to early detect a RowHammer effect. So you can basically connect a capacitor, maybe a separate capacitor, that acts as a canary, meaning the capacitor leaks much more quickly than other capacitors. And as a result, when that leaks, you know that something bad is going on. And I like that idea conceptually. I don't think anyone has implemented it at this point. But if someone can implement something like that, yes, it could be an early detection capability. Now, the problem is that designing that capacitor may be very hard, because we're talking about very small structures, and you cannot control the size of the capacitor and the capacitance of the capacitor accurately in the process technologies that we have today with that small size structures. So let me give you an example of the size. Basically, we're talking about 10 nanometers or so. So this is really even storing maybe a few electrons, right? Tens of electrons. So it's going to be very difficult to control the design of that capacitor. But I like the conceptual idea.
Okay, thank you.
Sure, you're welcome.
There is a question in chat box.
Okay, let me see. Should I read it? Okay, I'll read it. So it says, do you have any must-read book suggestions about computer architectures, computing, or about life in general? Oh, okay, very interesting question. So I think computer architectures, and frankly, I would recommend my lectures, as Ahmet mentioned earlier. You can even see the channel. I think that's my channel over there. I would recommend looking at my lectures as opposed to reading a book. There are a lot of books, but I think books are easily outdated. And that's one of the reasons why I actually wanted, well, this is one of the other side effects of putting things online, right? Every semester, I can update my lectures. For example, when I gave the lectures this semester, I was able to talk about Samsung's function in memory computer. which no book talks about, and no book can talk about, because you cannot update a book as frequently you can update lectures. So right now, this is a very fast-moving field. There are a lot of interesting things going on. That's why I would recommend looking at my lectures. And my lectures, I carefully designed them to cover cutting-edge materials as well as fundamentals. So if you watch, for example, the first lecture of digital design and computer architecture, or computer architecture, you will get a good overview of the field. And then you can you can basically go through all of the lectures and use the slides. You can actually complete the entire course if you're interested in that. Then you will get a very, very strong overview of cutting edge as well as fundamental computing architecture concepts. I would suggest, if you don't have any background, I would suggest starting with digital design and computer architecture, which I'm teaching right now. It starts from transistors as an abstraction level, and it builds up basically. It basically teaches how computers work. How can you design a computer? How can software get executed on a computer, etc. And then there's a computer architecture lecture that follows this one. That's why frankly, I would recommend going through the lecture so that you can be exposed to the cutting edge right away. Any book you read will be outdated. And in fact, there are many books clearly on computer architecture, and I like some of them. But for example, I like Harold Stone's book from 1992, but it's from 1992, right? I would not recommend that you read it to get an overview of the field. Maybe when you become more familiar with the field, then you go ahead and read some of the books. Then it becomes more interesting. But my personal advice, and I'm biased here because they're my own lectures, is to really go over the lectures. And perhaps you can ask other people who have gone over my lectures. So about life in general, I mean, there are a lot of books about, about computing. I think I would also recommend another book, which is my advisor's book, which I also use in my lectures. You can also see the books that are recommended in my lectures in digital design and computer architecture. For example, we use two books. One is Introduction to Computing Systems by Pentium Patel. This is the book that I learned computing from when I was a freshman in 1998. I learned computing from an older version of that book, and I would definitely recommend it. We also use Harris and Harris. So these are lower levels. For other books about computing, I mean, there are a lot of recommendations that I give in my lectures also. If you're interested, you can take a look at them. But one of the books is the Pentium Chronicles. It's by Bob Colwell, who was the chief architect of Intel Pentium Pro, which was a very innovative design at its time. And he talks about essentially the stories about designing the Intel Pentium Pro and the politics and the business and economics related to it. So it's a beautiful book about not just the technology, and it's also not detailed in terms of technology. Basically, it doesn't require a lot of knowledge, but it also talks about how they designed the chips, Pentium Pro chips at the time. And I like that book a lot, and I'd recommend it. There are also other books that I would recommend, but I guess we don't have a lot of time. I think one book that I will single out that I recommend to my students is Thomas Kuhn's Structure of Scientific Revolutions. You could call it a book about science or life. You can definitely get a lot of lessons about life in the Structure of Scientific Revolutions book. But basically, in this book, it's a philosophy of science book. And Thomas Kuhn really studies how scientific revolutions happen and what goes into it. Basically, for example, he talks about astronomy, right? People used to think the Earth was flat. I think sometimes today, even some people think the Earth is flat, but unfortunately, we need to resist them as scientists. But people thought the Earth was flat, and the first people who argued that the Earth isn't flat were killed or not welcome in the world. And he talks about basically how these revolutions happen in science. You move from a big paradigm to some other big paradigm, and the societal effects plus scientific effects that resist this sort of revolution, the scientific movements. And I think today it's important to read that book because science is clearly extremely important going into the future. And it's the only thing that we can rely on, in my opinion, as the basis of improving things, right? Because it has a specific method of answering questions and trying to understand things. And you have to really be critical and execute that method. And today, I think science is under attack by many, many people all over the world. I'm sure you're experiencing it in Turkey. I'm sure we're experiencing it in Switzerland, in the US, anywhere, basically. A lot of people are attacking science for not so good reasons, in my opinion, usually to deliver their political agenda. But I think this book is very good at distilling what's really important in science and how you can actually advance science and how revolutions happen in science. It's not an easy reading, but I recommend that to my students and everyone, actually. In fact, I used to give that as a present to students who do well in my programming assignments. And some of them have read it and they said they really learned a lot from that book. Okay, I mean, I'm sure I can have more recommendations over here as we go into literature, etc. But I'm going to limit it to these books at this point. Hopefully that's useful.
While you are concluding your lecture, we can take questions in chat box, or they can send me in private chat.
Sure.
I think, and we can also listen concluding part and also take a question. It can be efficient.
Okay, sounds good. So let me conclude. I'll try to keep it short. I saw some writing, so let me see. Okay, maybe I'll do that at the end. Okay, so basically, I will conclude with some quotes and some pictures. So hopefully it'll be fun. Some very famous architects said architecture should be based upon principle and not upon precedent. Precedent is what comes before. And I think I like this actually, because I think this is really applicable to a lot of things in life, not just architecture. If you really want to advance, you should really not think about what came before. You should really look forward and do better than before, right? And I think this is really based on principle. And this person was a very principled architect. His name is Frank Lloyd Wright. He is probably the most famous American architect. And because he was principled, he did not design this. This is an okay place, right? As you can see, he designed this masterpiece. And this is a better picture of it. This is very close to Carnegie Mellon University, where I used to teach at. And it's falling water, essentially. It's in the middle of beautiful nature, close to Pittsburgh. And basically, it's based on some design principles. And you can see that it's on a waterfall, and it's imitating the waterfall. And clearly, this design was really, really important. It's actually taught in architecture classes 101 in the world for its principledness and creativity also. Now that I'm in Zurich, I talk about this precedent-based design. So this is a train station that's boring, precedent-based. It's nothing like this. This train station in Zurich that was designed by another famous architect. So you can see that these train stations that are precedent-based are, okay, they work, but they may not be as good. This is more costly, but they give you a new way of thinking, let's say. It enables you to think bigger. It enables the world to become bigger overall. If the world had all these train stations all over, it would be a very boring place. And I think, sure, these work, but it's quite boring. It's these people who really come up with new paradigms of architecture with principled designs that enable the new future, let's say. And that's true for computing architectures also, I think. Another principled design from the same architect is this in Lisbon. This is in Valencia. And this is in New York City, the Oculus. This was designed very recently. So all of these are more costly, and they are paradigm shifts, in my opinion. So in order to actually experience the new paradigm, you need to pay for it. No question about that. And once you pay for it, though, it doesn't matter, because you've experienced something completely new, and the world is much better at that point. So this is the architect, actually. It's Santiago Calatrava, who is an ETH alumnus. So basically, my point here is there are principles for many different things. Do we have the overarching principles for computing? I don't know. And I think, but what I know is that what we use as principles today are not good enough. So processor-centric design is a dominant principle for designing systems today. But as I said earlier, it's extremely inefficient, unsustainable, low performance, complex, leads to a lot of complexity. And I'm very sure that based on my knowledge in biopsychology and neuropsychology, this thing, the brain, is not a processor-centric system. It's a more distributed, much more distributed system where you have logic and memory integrated much more closely together, where you can do specialized functions very, very efficiently without moving data a whole lot. And we don't quite understand it. And I think we should really do a lot to understand it. But we will see. So I don't think we have really discovered the key principles of computation yet. We know some good principles. I think some examples are this. I'm not going to talk about these in more detail because we don't have time. But I think more than anything else, we need open minds to apply these principles. So there may be a lot of principles that you discover, but you just need your open mind, scientific way of thinking, critical way of thinking to actually discover those principles so that you can actually make systems much better going into the future. So to conclude, I think it's time to design principled computing architectures to achieve the highest security, performance, and efficiency. We need to discover design principles for fundamentally secure and reliable computer architectures. And we need to design complete systems to be balanced and energy efficient, meaning data-centric or memory-centric and low latency. And we also want to enable new platforms for new applications like genomics, medicine, and health. I believe this can lead to orders of magnitude improvements. I've shown you some examples. This can make us fundamentally more robust, dependable, and secure. It can enable new applications and computing platforms. It can enable a better understanding of nature into the future as well. And who knows what else, because once you unleash new ideas and creativity, you can do much more. So I believe the future is very bright, regardless of all the challenges we're having in technology and problems, requirements. But to get there, we need to be able to think and act across the stack. The good thing is we can get there step by step. We don't need to change everything overnight, right? And again, I will conclude with some pointers to key papers that overall cover processing in memory, these two papers, and the lecture that I mentioned that was delivered at IEDM. So I will thank people who fund our research. These are, we are lucky to have been funded by many companies and institutions, as you can see, and all of my students and postdocs and collaborators who have contributed to a lot of the works that we have discussed. And more than anything else, I will thank people in my group whom you have seen earlier in this talk. And again, if you're interested in reading more, we have this January 2021 newsletter. That's the newest one that you can learn a lot from, hopefully. Okay, so at this point, I have concluded. Thanks for listening patiently. We took longer than expected, I think. But now I can take some more questions.
Thank you very much, Onur Mutlu, Professor. There are some questions in chat, and there are some in my mind, and also there are some in my chat box.
Okay, so should I start with the chat ones? Because I can see them, and then you can ask the other ones.
Yeah.
Okay, so let's see. Somebody thanked me for the suggestions and the amazing lecture. Thank you for listening. Atakan asks, how do you see the future of quantum computing in your research area? So that's a great question also. So quantum computing is something that's certainly very, very interesting, right? And people have developed quantum algorithms for decades. And today there's a huge push for enabling quantum computation. One of the problems with quantum computation to enable it in a real system is you need to operate at very, very low temperatures, right? 4 Kelvin, for example, that's very low temperature. And that requires a fundamentally different way of building systems and cooling systems. So that's going to be not so easy, in my opinion. So from an architectural perspective, I think it's good. It's good to do these efforts to enable quantum computing paradigms. And when it's enabled, I think quantum computing can lead to a lot of security issues also, right? Because now you can break a lot of cryptographic protocols that we have been relying on in our lives all over the place. So there's a danger over there as well, but we should push for it for sure. I think quantum computing, in my opinion, overall architecturally, is yet another paradigm. So we have processing in memory, for example, we have quantum computing. I think these are very interesting paradigms. We have graphics processing units, etc. There are other paradigms, systolic arrays, for example, that we talk about. Quantum computing is also good at some algorithms. Basically, I don't see quantum computing as being very general purpose. And I think even people who work on quantum computing realize that today. It's very hard to make it extremely general purpose. For some specific algorithms, for example, Shor's factoring algorithm, it's a great fit. You cannot do it easily with existing paradigms. You have to have a quantum computer for it. But for some other algorithms like databases, for example, or graph analytics, I'm not sure how good of a fit quantum computing is. In my opinion, it's not a great fit. So I think the future is when it becomes viable, which I think will still take at least 1 or 2 decades, in my opinion, even though companies claim that they have it running, etc. Usually they tend to be marketing claims. I think there's still 1 or 2 decades for quantum computing to really affect our lives, let's say. But again, it will be an accelerator. For some workloads, for some applications, it's going to be extremely good. No other paradigm can beat it. But for some other really, really important workloads that we're executing right now, it's not going to be important at all. As a result, it will be part of the solution for higher efficiency and not a complete solution that replaces everything. Hopefully that answers your question. And that's true for memories also, for example. As far as I know, there is no good memory that operates based on quantum principles today. So you may have a quantum computer, but you still need to have a memory system like we discussed today. Okay, so another question. Does Apple's M1 chip achieve any of the goals you mentioned in the lecture by gathering different units together? So that's also a very good question. So Apple's M1 chip, what it does is it has certainly a machine learning accelerator, a GPU, multiple GPUs, and then multiple cores, different types of cores, right? So it's very heterogeneous. So it exploits the principle of heterogeneity. So if you go back in my slides, for example, I had this principle of heterogeneity as part of the design principles. If I go back over here, I think it's one of the, as you can see, yeah, heterogeneity. So it exploits the principle of heterogeneity and better than worst case design by bringing things together. And it has large caches, of course. So it helps with efficiency for sure, but it doesn't create a fundamental shift like what we are talking about. For example, it doesn't help with fundamentally with security, reliability. It doesn't really change the paradigm of computation. So those caches are there, yes, but they cannot do processing inside memory, for example. You have to first bring the data inside the processor so that the GPU can work on it, neural network can work on it, neural network accelerator can work on it, and CPU work on it. So certainly it's more efficient and it's a good design, in my opinion. But again, it's not a fundamental shift like what we're trying to achieve. So when your workload is really, really intensive, it's going to suffer again. So hopefully that answered your questions. And we can move on to other questions that I don't see at this point.
You can also open your mic and ask. Are there anyone who wants to ask?
Okay, I want to ask a question about the RowHammer again. So
okay.
Since solving the RowHammer issue is somehow difficult, I wanted to know, like, if you have considered analyzing how memory is extracted. Maybe the problem might come from there, how memory is extracted.
But what do you mean when you say how memory is extracted? It's read,
How,
you mean?
like, yes, exactly, yeah.
Yeah. So yes, basically some of the solutions, I didn't talk about solutions. So I would recommend, since you're really interested in this topic, I'd recommend watching my lectures on the topic. You will find them very interesting. I talk about some solution directions, for example. I would also recommend the RowHammer video, for example, from my student that was recently published on our channel. But basically, yes, you really need to, if you don't solve the problem at the device level, a good solution is really by tracking the accesses to memory, access patterns, and limiting the number of times you read the memory within a refresh, read the same row within a refresh interval. And this is a solution direction that multiple works have followed. They basically keep track of accesses, try to understand whether somebody's trying to cause RowHammer with the access patterns. And if they think, if the memory controller, for example, thinks that an access pattern is malicious or it's going to cause RowHammer, they basically either throttle the accesses, like reduce the access rate to that row, or they try to do something proactive by trying to ensure that adjacent rows are refreshed more frequently. So I think certainly that general direction has been explored, and there's certainly more to do in that direction. And I think that's a good direction to try to solve RowHammer.
Okay, thank you very much.
Sure. And that's what I mean by intelligent memory controllers, by the way. This is an intelligent memory controller that tries to understand the access patterns and avoid the access patterns that lead to RowHammer.
Anyone else? Okay. I have in my chat box. Bioinformatics is also one of your areas of study, and frankly, I think it's the most interesting. Why are you interested in bioinformatics? How is it related to computer architecture? What kind of study on computer architecture do you think will improve bioinformatics?
Okay, that's a long question that requires its own lecture. Yeah, so let me tackle this. Basically, as I mentioned, this is a very important workload, and it's very similar to machine learning, in my opinion. Let me try to actually go to some of these slides where I talk about bioinformatics very quickly. I'm not going to go into detail, but basically, these workloads are so demanding from the computational devices and also memory that we really need specialized architectures for them. Let me give you an example from machine learning, actually, before I go into bioinformatics. So this is actually the companies that are doing machine learning chips. Machine learning is so demanding that all of these companies that would otherwise not design chips are designing chips, for example, for machine learning. And you can see there are many, many startups also. And this is an old picture, actually, that I copied from this website at the bottom. So these are some examples also. And as I said, Google is designing its own chips, for example. So if you go back some slides, I actually show chips that do machine learning, like this one, for example. This is another interesting one. So the workload is so demanding in terms of its computation and memory that people are really designing specialized accelerator chips to maximize the performance and maximize the efficiency. And bioinformatics is just another example. And I think bioinformatics is very general, clearly. There again, the workload is so demanding that we need to do something big in terms of the architecture, algorithms, and algorithm architecture, device co-design for it. And very quickly, this got started because I have a collaborator that I have a friend, actually, whom I collaborate with. He's John Alkan from Bilkent University. And when we were hiking in Seattle, in 2007, we basically were dreaming that we could actually design embedded devices that can perform comprehensive genome analysis in real time, let's say within a minute, right? Like answer very, very interesting questions like this. You give this device to a doctor, for example, and doctor quickly tries to figure out what is the likely genetic disposition of this patient to this drug and this drug and this drug and this drug that I'm thinking of, so that they can personalize the treatment for the patient, or what disease this particular DNA might be associated with. You can actually do profiling of microbiomes all over the place to do outbreak detection and prediction, etc. So basically, you can prevent a lot of the outbreaks that we have to deal with right now if you're more intelligent about genome analysis in the wild. So there are a lot of interesting applications, and that was the major reason why I was very attracted to it, basically. You can imagine many, many applications, good applications, health, medicine applications, but also other applications that can enable a much better understanding of life in general. If you actually are able to have a device that can do very, very comprehensive analysis and answer very, very sophisticated questions in real time within seconds or minutes. And that's exactly why we're doing bioinformatics, actually. As I said earlier, in 1990s, I was also interested in molecular biology and genetics. And I was always interested in genetics and how it affects our lives. And that was one of the reasons why I restarted this in 2007, as you can see over here. So that's the main reason, basically. That's how it relates to computer architecture, because I'm going to skip some of these slides over here, but you can watch some lectures. Basically, we have a huge problem in computing systems today. We're very much bottlenecked by computing systems today. And the work that we have done has tried to accelerate that bottleneck and get rid of it as much as possible. because you're really bottlenecked by the algorithms and the devices, as you can see in these pictures. Okay, I'm not going to go through all of these, but basically we have been looking at FPGA designs that can accelerate these bottlenecks, and you can read some papers. These are also all open source, as you can see. And you can see in-memory processing designs and algorithm architecture co-designs in these works. So if you really want to be very high performance, you need to co-design the algorithm and architecture, and also efficient, right? Let me quickly also talk about the future of this a little bit. So future of this genome sequencing and analysis looks like this, basically. You have very small devices that can sample a genome, and you need to analyze it. To be able to analyze it efficiently, you need to have computing units that are very specialized for the questions that you're asking to it. And this is applicable in many, many systems. And one example is coronavirus, COVID-19, for example. This is actually an example I used in my class when I was teaching in February 2020. So these sequencing devices were some of the first things that were shipped to China to actually understand what was going on with COVID-19. And I think Chinese folks actually did a good job in understanding it, probably. But I'm not going to go through details. So there's clearly a lot of really, really interesting and exciting applications of this sequencing devices, but we need to really figure out how to build both algorithms and architectures to enable these devices. And again, if you're interested, you can take a look at this paper that talks about essentially the question that you asked. And again, this lecture that I delivered recently gives you a reasonably fast overview in 1 hour, 30 minutes over here. But that's a very good question, basically. And we have more information in our more detailed lectures over here. So hopefully that answers your question.
Thank you very much.
I'll keep this over here so that you can look.
Are there any else?
I see one more thing in chat. Okay, that says thank you.
I think Onur Mutlu is disconnected. He's one of...
Can you hear me? Hello? Hello?
Hello, yes, I think we can hear you.
Okay, okay.
I lost connection.
Okay.
So sorry about it.
I can hear you now.
Okay. Are there any else who want to ask question? If there is no any other question, we are here.
I'm sorry, I want to ask a last question.
Yes.
I'm an electrical and electronics engineering student. Can I also learn these things about hardware, or it is not related to my program?
Of course it's related. So you can certainly learn. You said you're an electrical and electronics engineer, right?
Yes.
Yeah. These are certainly things that you can learn. And again, what I described really spans both low levels of the computing stack, which is really electronics and electrical engineering, to the high levels, which is algorithms and software. So I think anyone who is really interested in solving important problems, interesting problems like this, can learn. But certainly with electrical engineering, you can learn about this. And I would actually recommend anyone not to stay in the levels that they're comfortable at, but actually broaden their knowledge toward the directions that are interesting. Because again, the future is really about being able to operate really well across the stack, algorithm, architecture, hardware, co-design. So I would definitely, you can definitely learn, and you would actually have the fundamentals to learn it, because in the end, if you know about electrical engineering, you just need to build up, right? Hopefully that's helpful.
Okay, yeah, Thank you.
You're welcome.
Sorry, can you hear me?
Yes.
Okay, I have one more question.
Sure.
I guess it will be the last question. Do you have any position for international students in your research group at ETH Zurich? I don't know very much about it, so I wanted to ask.
Sure. Yeah. That's a good question. And the answer is yes. I always take students. I mean, our group is actually very, very international. If you look at this slide, for example, it gives you an idea of how international, and this is not the entire group, but we're quite international. We have people from all over the world that is part of the group. And we also have students who are remote interns, remotely joining us, especially these days. Remote internships are a possibility. So certainly, I'm always looking for students who want to do strong work and who are interested and excited about these topics and who want to do something big to solve problems. And I would recommend if you or anyone else is interested, you can apply through our website. If you go to our newsletter here, you can see that we have a website and we have an application. Actually, maybe I can share it. I don't know. Let's see. Okay, it says advanced threat protection. I don't know. So if you go to my website, maybe I'll share my screen very quickly. So I'll share okay, you're seeing it right now. So this is my website. You can easily reach it by Googling me, for example. And you can also go to my research group website, my research group over here. Clearly, you can see the YouTube channels, etc. as well. But if you go to our research group website, this has a lot of information about our group. And you can also see people in our group. You can see names and you can guess where they're from. So it's quite international. As you can see, we have affiliated researchers. We also have interns over here. And you can see a lot of things like courses, publications. It's even updated. It's relatively recent, as you can see over here. So you can see work with us over here, for example. This talks about what to do if you want to apply. You can click apply here, which brings you to a website that essentially asks you to create an account and fill out some information to apply. And I would also recommend taking a look at publications, certainly what we work. I mean, you've already seen what we work on, but you can see more over here. The publications list a lot of things that we work on, but we also have thesis and projects. You can do bachelor's, master's, and semester projects. This is normally open to ETH students, but if people want to work on these things remotely, and if they interview with us and everything is good, then you can actually work on it remotely as well. And you can see there's a variety of projects that are not limited to what's over here. We have more projects than what's described over here. Hopefully.
Thank you very much for your answers.
Okay, you're welcome.
That's great. Thank you.
Sure.
I think Ahmed lost the connection.
Okay.
It was a pleasure to host you today. It was a really nice talk. Thank you for joining us. And thanks for the participants for their questions.
Okay, thank you very much, Nejla. I enjoyed it.
I guess then this is the end. Ahmed, do you hear us? Do you want to say something?
I am back.
Cool.
Thank you very much, Professor Onur.
Okay, thank you very much, Ahmed.
Pleasure, great pleasure. And we can stop recording.
Okay.